Okay, now we're going to try the last method. That will be to do pole zero cancellation. So that will be pole zero cancellation. And for that we have another cadence template. So let's just save this one. Close. Okay, so we're going to use this one. And then, as you can see here, yeah, I just load the output of the first stage with the resistor in series with the capacitor. So that will be the pole zero cancellation. We launch ADXL. So it is exactly the same as before. It's just a copy of the same design, but with the addition of this compensation. Now let's do some quick calculations. Then we are going to move. We're just going to use brute force to move the low frequency pole to a lowest frequency. And we're going to do it is that we're going to add a large capacitance. How large? Well, it will depend how much do we need. We are going to start with around 40 times the value of CGS2 plus CDS1. So that is the capacitance that is loading the output of the first stage, and you typically will have to iterate until you get reasonably good splitting of the poles, so the separation of the poles. So we're going to start with this value 40, and you will check that the capacitor it is not very large also, because if it is very large we are not going to be able to implement it on chip. This gives a value of 2.58 picofarad, and then you already start noticing something. For the Phantom Zero I needed around 40 femto. 40-50 femtofarad is a very small capacitance that needs to be added outside of the amplifier. For the Miller compensation, I had to increase that value a little bit. I mean, it will depend pretty much on the gain of the second stage, on the amplification of the Miller amplification, but typically will be a bit larger. It can be hundreds of femtofarads, or very often even we can reach picofarads. But the pole zero cancellation will be much larger, typically, much larger. In this case, it doesn't look very large, but it can reach very large values. So in this case, it's 2.58 picofarad. And then the position of the first pole, now I can just recalculate. That will be -1 divided by 2p RDS, and that will be all the capacitance here. That will be this compensation capacitance plus CDS1 plus CGS2 plus CDG1, and then I will have plus CGD2. Actually, this is CGD1. That will be CGD2 multiplied by the Miller effect. That will be RDS2 in parallel to R1 plus R2. Okay, and then in this particular case, since I am loading, we see the circuit here. I will be loading with a lot of capacitance here. That will basically kill the pole splitting, because then we will not have anymore these interactions. So they will be basically shorting the gate to ground. This very large capacitance will be shorting the gate to ground, and we will not have this interaction that we see here. So that will not happen to the large value of this capacitance. So I don't have to worry if I am taking in consideration the pole splitting or not, because it will not happen. So okay, we have this position of this pole here, and when I calculate this pole, that will move to minus 14.2 kilohertz. Then the second pole will be located at minus 1 divided by 2 pi RDS2, and the top is RDS1. This is RDS2, that is in parallel to R1 plus R2, and all of this will be multiplied by the capacitance. Which capacitance? That will be the output capacitance, CDS2 plus CL. And again, there is no this pole splitting anymore. The pole splitting has been killed by this large capacitance, that it is basically shunting the gate of the second transistor to ground. So then we have the second pole, and then that will be do the calculation, minus 1.4 megahertz. Okay, and then I will add the resistor, the 0. If I add this resistor in series to the compensation capacitor, the 0 that will appear will be located at minus 1 divided by 2 pi compensation capacitance and the compensation resistor. And then if I put this 0 exactly over the second pole, then I can calculate the resistance. That will be 2 PCC P2, and that value I get it is 54 kilo ohms. Okay, the value that I'm getting is 54 kilo ohms. So let's take a look what happens if I plug in these values in the circuit. So I get it 54 kilo ohms here. The capacitance that I'm getting is 2.5 pico, and then let's just run the simulation. Then let's take a look what happened here. The closed loop gain, we have the system has been stabilized and actually has a pretty decent gain. Okay, so let's take a look to the 3 dB bandwidth. We got gain above 30 megahertz, which is pretty good. The position of the poles minus 17.23. So, and yeah, very close to Butterworth positions actually. So managed to do a pretty good job by stabilizing this amplifier. So let's take a look to AB. We get this log scale, and though I don't have the phase here, but now I think it is a good moment to take a look here. What is the impact of adding this compensation? So take a look that now we will have a pole in the loop gain located just above 10 kilohertz. Okay, and then it's going to start filtering the loop gain here. And so the same as with the Miller, I am losing loop gain at high frequencies. That even though I may have a quite good result with the bandwidth, I might be degrading, for instance, linearity, because the loop gain is corrected with the linearity is corrected with the loop gain, and if they reduce in the loop gain here at high frequencies, that I may run into trouble when I run the linearity tests. Okay, so we have tried the three types of compensation technique: phantom zero, Miller compensation with pole zero splitting, and also the compensation using pole zero cancellation. We have a script that summarizes this exercise, and that basically do all the calculations that I have done by hand and on paper, and it gives us the summary of the pole position before compensation. It calculates the compensation values that I need to put for the phantom zero, for the Miller compensation with the pole splitting, and also for the pole zero cancellation. So you can take a look to the script that it is going also to be available as part of the material.